Look upon my calculus, ye mighty, and despair. Nothing beside remains round the rates of change of that polygonal surface, bounded and bare, the lone and level triangles stretch far away. For obvious reasons, I wanted to do a video related to calculus on or around Halloween, but real life had other ideas, some stuff got in the way, and, well, we're doing it now. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and let's talk about some shader derivatives. So if you were traumatized by calculus in high school or beyond, don't worry, we're not going to be doing anything really, like, horrifying, like actually computing the rates of change ourselves. We are going to be using some shader functions that will compute the rate of a change of a value for us in the shader, and we are going to just look at some of the things that we can do with them in this video today. So about almost 2 years ago, I made a video on outline shaders using a Sobel kernel. That being a fancy word for just a little image filter that you pass over every pixel of an image, and it can compute whether or not there's a gradient at every pixel, and it will do that to detect an outline around an image, such as that little bunny icon. And today we're going to be doing something that has a similar outcome to that, but using a different strategy. So, if I were to open up the outline shader, the only part we care about is the fragment shader. We're not going to be touching the vertex shader the same way as last time. So before I explain how shader derivatives work, we're going to need a quick crash course in exactly what happens on the GPU when you render something. So graphics cards, you may be aware, are pieces of hardware that are very good at doing simple operations in parallel. And that really helps when it comes to rendering stuff, because that means you can have the graphics card process multiple vertices at the same time. When it comes to the fragment shader / pixel shader, you can have the graphics card render multiple pixels at a time. And that works because, generally speaking, each vertex and each pixel doesn't really care about what's happening to its neighbors. And if you're trying to render thousands and thousands of pixels per frame, your graphics card can just look at that, say, no problem, I got this, and it can just do everything in a massively parallel operation. And at the heart of all this, when it comes to rendering pixels, your graphics card will work on tiny, tiny units of pixels at a time. I believe the individual clusters of pixels that are worked on in like one single unit are just a 2x2 square, so 4 pixels at a time in a 2x2 square. The second important point about how graphics cards work that is relevant to us today is that each of the graphics card will do its darndest to make sure that each of the pixels that is in one of these little units will have all of its shader code executed perfectly in parallel. This is called lockstep. And this has some implications if you've ever heard that in a shader, if you have an if statement, both the if and the else blocks of an if statement will be executed. This is where that comes from. Whether or not that's true in all cases is a whole matter of debate that tends to lead to a lot of screaming on the internet and is honestly not really what we care about doing right now, so I won't be getting into it. Anyway, given these two little details about how rendering works in the modern day, while it's not possible, and a lot of people do ask if it's possible to do this, it's not possible to directly get the value of what's happening in any adjacent pixel and any neighboring pixel in the fragment shader. It is possible to get the gradient of any particular value at any moment in time in the fragment shader. And this is where partial derivatives come in. First, maybe for a bit of a visual example, so if I have 4 pixels on the screen, and let's just say they look like this, and we'll just get the gradient of the colors just to make things easy. Let's say the pixel in the upper left is black, and the pixel in the upper right is another color, let's say red. And in shaders, of course, black has a color value of 0, 0, 0, and red has a color value of 1, 0, 0. And if you wanted to get the gradient, that is the change in the color value across the horizontal set of these pixels from left to right, you can ask the graphics card for the change in this value, in this case the color value, on the horizontal axis, on the x-axis. And in this case, you can work it out in your head. The rate of change from black to red is going to be a value of 1, 0, 0 going up in the horizontal direction. If the color in the lower left corner was another color, let's say cayenne, so sky blue, that would be a color value of 0, 1, 1. And if you wanted to get the gradient, if you wanted to get the change of that color value in the vertical direction, then that would simply be the difference between the color in the lower left and the color in the upper left, and that would be a change of positive, well, 0, positive 1, positive 1. And if the color in the lower right was, let's say, another color, let's say, I don't know, 50% gray, so 0.5, 0.5, 0.5, you could also get the gradient, you could get the partial derivatives on the horizontal or on the vertical axis between the color in the upper right, which in this case would be negative 0.5, 0.5, 0.5, because that is the difference in the color values. Or if you wanted to, you could get the gradient on the horizontal axis. So going from cyan to 50% gray, that would be positive 0.5, negative 0.5, negative 0.5, and that is going to be the rates of change of those values across each of those 4 pixels. And you can do this with any value in a shader. You can you don't have to do this with a color value. You could do this with any old value. And this comes up useful in all kinds of places. So getting back to GameMaker and getting back to GLSL, let's write some code. And I'm going to, I think, get rid of all of this. I will, however, let's see, I will sample from the GameMaker base texture because that is going to be the color, the set of values that we're starting with. And I can call this vec4 starting color. And if I wanted to produce an outline, actually, before I get to that, let's just say that before I get to that, let us take the partial derivatives in the horizontal, vertical, and combined directions of this starting color. And let's just see what happens. So I can get rid of this line too. The functions of relevance to us today are going to be dFdx, dFdy. I believe these need to be capital F dy. And there is a third fwidth. You can probably match dFdx and dFdy onto the example that I gave a minute ago. Fwidth sounds a little bit different, and I feel like I spelled that wrong. Fwidth, I believe is what it should be. I feel like I yeah, definitely spelled that wrong. I'll get to what that is in a minute. So the partial derivatives, dFdx, dFdy, and fwidth, are going to return. They're one of the functions that will return the same type that you input into them. So if you input a float into one of these functions, then the return value will be a float. If you input a vector into one of these functions, then the return value will be a vector, with each of the channels of the vector being the gradient on that channel. So if you were to take the partial derivative of a color of a vec4, then the result would be, as stated in that example, a color value representing the difference, representing the gradient. And unfortunately, if I were to say, let's just go with float. I'm going to be, this image that I'm going to be using, this is grayscale, so it's going to be red, green, and blue are all going to have the same values, and I'm just going to make this a float to make it a little easier. I can say float diff for the difference or something like that. It can be dFdx of starting color.r, and the final image. And again, I'm just going to make this like a black and white outline. The final image can be whatever this value is turned into a color. And this isn't going to work. There's a couple issues with this code, and I'll get to them one by one. The first is that if I were to just run the game, and can I make the text in this console a little bigger? That's pretty small text. Output windows, where is the output? I can make this like, let's make that size 24. There is a shader error, and if I were to look up in the console for some hints as to why that might be, you're going to find something to the effect of GLOES standard derivatives extension is disabled. And this is one of those things that I really hope that I can say in a video and it'll just be like completely out of date soon. Because GameMaker's version of OpenGL that it's using, GameMaker's shader version that it's using is something like GLSL ES2, which is equivalent to like GLSL 1.2 or something really old. And an awful lot of modern like shader languages, this is something that's just enabled by default. But because GameMaker just is the way it is, we have to manually enable it. And I believe that the way you would do that is, the keyword is pound extension. Boy, the syntax highlighting for this shader editor really doesn't want to work today. Anyway, GL underscore OES underscore standard derivatives colon enable. And this will enable the, basically, this will enable the use of these standard derivative functions. It is, in this shader version, an extension. And you have to enable it like this. There's a whole bunch of OpenGL shader extensions. Standard derivatives is probably by far the one that sees the most use. Anyway, once I do that, we can see that we have something resembling the outline of this bunny. And we can see that it's the outline is a little bit funny in places. We can see that it's only really happening on the right side of this bunny over here, which is a little bit strange. You can see the copyright text on the bottom of the image has turned a little bit strange. And looking at the original image, which is going to be this one, you can start to imagine how the rates of change and the gradients between pixels is going to start producing a result like this. So, for example, this is a fairly simple example. This edge over here goes from black to white. So that is pretty similar to the verbal example that I had that I did at the beginning, where going from black to white is going to be a change of more or less +1, +1, +1. When you convert that, or at least take the red channel of that and turn that into a color, we're going to have a white color on the outline on this side. If you were to go to the other side of the bunny, also the black to gray is going to be, of course, a fractional value between 0 and 1. Anyway, if I were to go over to the other side of the bunny, we're going to be going from white to black instead, and the change from whitish to blackish is going to be some negative value. And if I try to turn that into a color, it's not really going to work very well. I could always use the absolute value of that value, and we're going to see that we now have a gradient on the back side as well. Although we're not going to have as much on the top and the bottom because we're only checking for the horizontal gradient over here, and there's not as much of a vertical gradient on the top of the bunny. Or rather, there's not as much of a horizontal gradient on the top of the bunny. It's really all on the vertical. If you wanted to check for the vertical gradient instead, you could use dFdy. We're going to restart the game. And we're going to instead have the outline be a lot more prominent on the top and the bottom of the bunny, and not so much on the left and the right sides. And of course, if you wanted to account for both, you could say absolute value of, I'll do it in here, inside the absolute value. You could say dFdx plus dFdy, starting color.r. Take the absolute value of that sum, and we are going to have a pretty strong outline around the entirety of the bunny. There's only a couple places where you really don't see anything here. I guess you could add together the absolute values separately. Actually, that came out pretty similar. This expression brings us nicely to the fwidth function. And the fwidth function is essentially exactly this. It is the sum of the partial derivatives, so it's the total derivative, I suppose one might call it, of the rate of change of the value that you're getting the change of on the x and on the y. If you wanted to do this, you could also simply say fwidth of the starting color.r, and then you don't need any of this other junk. And if you were to run this, it would come out looking exactly the same, even right down to the weird bands in exactly the right places where the rate of change on the outline is very low, like on the bottom of the foot over here. And these are the shader derivatives. There's not much more to these themselves, but you can use these for all kinds of things. As you saw, we use this to produce a rather rudimentary outline. And for what it's worth, if you wanted to do an outline, the Sobel filter probably produced a more, shall we say, reliable answer. The outline was definitely thicker, and by tweaking the values inside the Sobel kernel, you can fine-tune the outline in different ways. Whereas this is really just literally just getting the rate of change over a single pixel, and it's not really filtering anything or anything like that. On the subject of performance, because everyone always likes to go here in shaders, partial derivatives are actually really, really cheap to compute, because all they're not doing any fancy mathematical operation. They're not doing any fancy like iterative process the way that we were with the Sobel kernel and iterating over the Sobel kernel for every pixel. All they're doing is peeking into adjacent pixels and returning the rate of change across the little clusters of pixels that are being processed at any given time. And if you're worried about the fact that derivatives in high school calculus kind of annoying, kind of took a long time to compute by hand, especially because you had to analyze the equation that you were given and do different things to it to come up with the derivative, or God forbid, do it iteratively using limits and stuff. Shader derivatives aren't like that. Partial derivatives are only going to basically peek into the adjacent pixel, subtract the appropriate values from each other, and return the difference. They're very nice. However, I should also throw a bit of a warning here because GameMaker's shader version is so old, and because the standard derivatives are not enabled by default, this may not work on all target platforms that you try to export to. I don't off the top of my head know which platforms this will work on and which they won't. I know it'll work on Windows. Obviously, I'm running this on Windows. When you run a game on Windows in GameMaker, it will convert your shaders to HLSL for DirectX anyway, which are a little bit, let's say, just a tiny bit more standardized, and you can generally count on certain things working on DirectX on Windows. I do not have a Linux device set up for testing and for capture on hand at the current moment, so I can't run this on the Raspberry Pi right now. I suppose I can always run this on HTML5 and OperaGX and just see what happens. Okay, it gave me a warning in the HTML5 window that said extension not supported, so this does not work on HTML5. Let's try OperaGX, OGX, which is generally better than HTML5 when it comes to running things, but it's I think it still runs on WebGL. Okay, cool. This actually does work on OperaGX. If it works on OperaGX, I'm inclined to believe it'll usually work on Linux, at least on Linux desktop. Hey. Let's see, what else is there? You might also remember from high school calculus class that it is possible to take the derivative of a derivative, the derivative of a derivative, which will be the second order derivative, the acceleration. You might try doing something like fwidth of the difference here, which is basically the fwidth of the starting color.red, or something like that. But that's not really going to produce a useful result because, again, we're not computing a mathematically perfect derivative value here. We're not computing the exact rate of change. We are simply peeking into our neighboring pixels, which are currently in the middle of being processed, and checking the value. I'm pretty sure this will just return 0 all the time if you try to return the derivative of a derivative. I can't think of many reasons you'd want to do that when it comes to game design, but, you know, just for science. Let's see what this produces. Pretty sure this is just going to be a black image. Yeah. So the derivative of a derivative in this case just returns 0. Let's see. So there's a couple other uses for this that I'm probably going to make videos in the, I can't say the near future, but eventually. Drawing wireframes in 3D. There's a couple ways to draw wireframes in 3D. I've made videos on some ways that you can do that in the past. But there is probably my favorite way, which involves shader derivatives and something else which is called barycentric coordinates. When it comes to 3D lighting, it is possible to compute the normal of a surface using shader derivatives in the fragment shader. And that can save you a little bit of trouble of having to calculate the normal of a vertex on the in a modeling program, and then import it into GameMaker, and then transform it in the vertex shader in accordance with the world normal. It is slightly easier to compute flat normals for 3D objects using shader derivatives in the fragment shader, especially if you're going to be doing the lighting calculations there anyway. And you can also use that to figure out things like tangent and bitangent vectors for use in things such as normal mapping, which is especially nice because then you don't have to do things such as spend memory on vertex attributes for multiple normal vectors in the vertex shader. That only works for flat shading though. If you want to have smooth shading on an object, that won't really work. But that's a story for another day. Oh, also HLSL. So in GLSL and HLSL, sometimes common functions have slightly different names, and by sometimes I mean probably most of the time. It's a little annoying, to be honest. The equivalent to dFdx in HLSL is going to be just called dDx, which honestly is probably a better name because you don't have to insert a random capital F in the middle of that function name. dFdy in HLSL is going to be dDy. And I had it open on my notes a minute ago. Fwidth in HLSL, I believe, is just fwidth. That one is the same name. So if you're writing shaders in HLSL, one, you don't have to do anything to enable shader derivatives in HLSL. They're just there automatically in HLSL 11. And two, these are the function names that you're going to want to use. Which is actually a rare instance of HLSL being less verbose than the equivalent GLSL, but you can use whichever you want. And lastly, this only works in the fragment shader. I feel like this should be obvious based on like my explanation of why and how this works that I talked about at the beginning of the video. But you can't use shader derivatives in the vertex shader. That doesn't make sense. The vertex shader works differently. You can't just peek into neighboring vertices in the vertex shader to see what's going on. So I'm going to let this outlined bunny be my example. For this example project. If you want the code for this, look for the GitHub repository down in the video description. Feel free to mess around with this. Feel free to see if there's anything else you can think of that you can do with shader derivatives. I hope you like them. They're not something that get talked about often in GameMaker, but they can be rather nice sometimes. I try to post about 2 game dev videos a week, one tutorial like this, and one let's make a game. I'd like to talk about some of the weirder things you can do in GameMaker, this video being a prime example, so if you're interested in weird shader stuff or 3D stuff or whatever, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I hope you all enjoyed this, and I will see you all later. You know what? Let's end this video in style. Let's use this to draw the outlines of the actual picture of my bunny. So that's gonna be that guy, a little lump, and you can use shader derivatives to draw a picture of him in outlines. He unfortunately died a few months ago, but his lasting contribution to science is going to be the test subject for drawing a bunch of outlines in a shader using shader derivatives. This got weird real fast. I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Harold Guidry, Jonathan Bernardez, Kiexi, Sindra Larson, Squarecrow, The Oz, and Zenjamin for supporting these videos. If you want to support the channel, head on over to the Patreon page down in the video description to join the fun.